All right, we're back with Stoke's theorem, and in the previous video we saw that we did the line integral around the boundary of a surface, and we got the value of -9 when we did all three of the boundary curves here. Now we're going to take a look at, do we get the same value when we do the right hand side of this? So we got to find the curl of our field dot in ds. Now a quick little reminder, this surface here was defined as 2x plus 2y plus z is equal to 6. And the field that we were using was -y squared was z and x. That was our field that we were using for this. So let's go through and now take a look at this side of the integral. Now, only a few things we need to remember is here, our normal vector has to be in the direction of your thumb when you traverse around the boundary in a counterclockwise position. So in a second, we're going to see that our normal vector has to be going somewhat in that direction. That's going to help us figure out which normal vector we want to use. All right, so the major part of this, let's see if we can find the curl of f. So the curl of f, remember, is del cross f, which is going to give us I, J, K, partial with respect to x, partial with respect to y, partial with respect to z, and our field is -y squared, z, and x. All right, in the I direction, let's see, it's going to be the partial of x with respect to y is 0 minus the partial of z with respect to z is 1. So that is in the I direction. Minus, in the j direction, we get the partial of x with respect to x is 1 minus, and in the y direction we get, in the other direction, we get the partial of -y squared with respect to z, which is 0. In the k direction we get what? The partial with respect to x of z, which is 0, minus the partial with respect to y of -y squared is -2y. All right, so the curl of our field is -1, -1, 2y. All right, so that is the curl. Now we got to find our normal vector. The way that we always been finding our normal vector, remember this is del g over the magnitude of del g. And g was defined to be when we took our surface and moved everything to one side, basically. Now we want to move everything to one side to make sure that we have the right normal vector. Now you can notice here that everywhere on the surface, the z component has to be positive. So we're going to define our big G of x, y, and z to be when we move everything to the side that keeps the z positive. So 2x, 2y, z minus 6. So now we should be able to find our normal vector fairly quickly. Let's go over here, and of course our normal vector will be del G over the magnitude of del G. So what do we end up with? So the gradient of this is 2, 2, 1 over the magnitude of that. 2 squared, 2 squared, 1 squared. So our gradient is going to be 1/3, 2, 2, 1. Okay, so now that we figured out what n is, the last piece we need to do here is figure out what ds is. So ds is a small piece of the surface area. So we need to decide when we do this which way we want to define our curve. Do we want to solve our equation for x, y, or z? Well, in this case, this would be easiest if we solve for z, so that's the way that I'm going to do it. So if we go ahead and say z is equal to 6 minus 2x minus 2y, now remember this is our little g of x and y, the way that we defined it in the past, then ds is the square root 1 plus g sub x squared g sub y squared dA. We're going to remember what that dA is here in a second. Okay, when we plug this in, ds is going to be the square root 1 plus -2 squared -2 squared dA, which we're out of room. This is just going to be 3 dA. That gives you 9, and square root of 9, of course, is 3. Okay, so we have almost all the pieces that we need to plug into this formula. We have our curl, we have the normal vector we want to use, and we have ds. The only thing last, that we're going to see in a second, we've got to figure out what a is. So I'm going to go back over here and see if we can set this up. I'm going to try to squeeze it right here to give us a little bit more room. So I'm going to do the double integral of the curl, -1, -1, 2y, dotted with n 2 to 1 over 3, or 1/3. Let me put the 1/3 out front. 1/3, 2 to 3, 2 to 1. Dotted, I'm going to say times 3dA. All right, so since we got that out of here, let's get our curl going. Now, what is the region dA? Because now it's a region. Well, since we decided to do our ds using x's and y's, that means dA has to be a dx dy or dy dx, because that's where we push this down into. So the region that we need to integrate across is in the xy plane. So if we look at our region, 1, 2, 3, 1, 2, 3, that's the region that we're going to have to integrate across for this integral. So let's clean this up and see what we end up with. Double integral over the region, when we 3 and 1/3 cancel, we do the dot product, I get -2 plus 2y dA. With the double integral of the region of -4 plus 2y dA. Okay, so let's go ahead and set up the bounds for our region. Again, we can do this dx dy or dy dx. Again, I'm going to use the same reasoning that I have in the past. If I do dy first, that means I'm going to integrate a y and I'm going to get a y squared. Then I'm going to have to plug in a function of x, which means that might be a little bit uglier. So when I set this up, -4 plus 2y, I'm actually going to go dx dy. Now remember, as we saw before, our equation for this surface, let's stick it right here, remember, was 2x, 2y plus z is equal to 6. Since this is in the xy plane, z is equal to 0, so this is 2x, 2y is equal to 6, or x plus y is equal to 3. So what does x run from in this region? It always runs from x equals 0 over to that line. So x goes from 0 to 3 minus y. And if we collapse this into the y direction, y goes from 0 to 3 when it collapses over. All right, so let's see if we can make our way through this. We integrate with respect to x, let's see, 0 to 3. That gives me -4x plus 2xy, evaluated from 0 to 3 minus y. Still need to integrate with respect to y. Top endpoint minus bottom endpoint, so that gives me -4 times 3 minus y plus 2, 3 minus y times y. Now the bottom endpoint, since every term had an x in it, is 0, so you don't need to put that. There's your -0. Let's clean this up a little bit. So that's -12 plus 4y. That's really a 2y that we're distributing, so plus 6y minus 2y squared. So from 0 to 3, I get -2y squared plus 10y minus 12. All right, one last little integral to do. So integrate each one of these. We get -2/3 y cubed plus 5y squared minus 12y, evaluated from 0 to 3. So -2/3 times 3 cubed, 5 times 3 squared, 12 times 3, minus the bottom endpoint. Everything has a factor of y, so again, that is 0. So what do we end up with here? One of these 3's cancels. That gives me 9 times 2 is -18. Plus 9 times 5 would be 45, minus 3 12s would be 36. So that's going to be negative, look at this right here. So we get -54 plus 45, which is -9. All right, so that's the result that we wanted to see from this, because we had already done the line integral and got that same value. So like all of our integral theorems, the real power of this is you can use either side to come up with the same result. So if the line integral is particularly difficult to do, maybe the right-hand side of the curl.nds might be a little bit easier. It just kind of depends on what you're happening, but you have this nice option to be able to use either one of these to find your result.